let's flesh out our assumption, and let's make sure that my audience understands what I'm trying to get across here. We're going to define B such that it is of any level of countability in our system. Aleph Nought, Aleph 1, Aleph 2, and B is what we're going to feed into the algorithm. That's our input, okay? So my assumption is that all algorithms of finite steps applied to B, okay, B can be within the Aleph Nought system of countability, within the Aleph 1 system of countability, or the Aleph 2 system of countability, and so forth, however many levels of countability we have, such that B becomes f of B, have results that are either countable or uncountable with respect to B. Pardon me, this should have been a B. Let me change that. Okay, not with respect to real numbers necessarily, but with respect to B. So we have no levels of countability within the algorithm itself. Okay, so we have levels of countability above, let's say, outside of the scope of the algorithm, but we have no levels of countability within the algorithm itself. So, notice that back when we were proving that R is greater than N, we would feed in N, essentially, Aleph Nought being the level of countability of N at infinity, feeding it into where we had our initial assumption of Aleph Nought rows, where we took our diagonal and we took our first digit of the first row, the second digit of the second row, the nth digit of the nth row. We took out that diagonal, and then we changed the diagonal, and then we reinserted it and we repeated it and over again. You can count either 3 steps or 4 steps, but the bottom line is we have a finite number of steps that repeat themselves over and over again until they terminate at uncountability, where it's not going to go any further because there's no such thing as steps any longer. We don't have anything discrete. And so we have uncountability at Aleph 1. Well, we also have, if you notice, uncountability at C2. Okay, so theoretically, if we repeat that algorithm over and over again, we should arrive at C. Now, if we assume that within that algorithm itself there are no degrees of countability, that it's either countable or uncountable, we have arrived at a situation where Aleph 1 corresponds to C. That there is no difference essentially between Aleph 1 and C. We've constructed an algorithm such that we have obliterated any possibility of there being degrees of countability between Aleph Nought and C. Now, this is a radical assumption, and this is not going to be accepted by all of you. And really, I repeat again, this is a philosophical argument and not a mathematical proof. But I want to show you how, in some sense, there are similar arguments that we use, not so much maybe in set theory, but in regular math that would verify. If you think about it, it's not an unreasonable assumption to make. If I have a number here, that would be 0.285567, and we're going on to infinity. That is a certain number on the real number line that is you can think of it as a point, or those of you who don't like the idea of that being a point because it leads to certain contradictions, that's fine. It is a number on the continuum. Okay. Well, you notice with B, if I were to have that very same number and then I were to somehow have dot, 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 and then another set of numbers here, that would not be accepted by mathematicians because A would be functionally speaking the same thing, but B, it would be like saying that we arrived at the exact precise number and then we're adding more to it. Let's say I had Aleph 1 decimal points. That wouldn't make any sense. We wouldn't have it. So it either is a number of Aleph Nought digits, or it is a number that effectively terminates. Once those Aleph Nought digits arrive at something beyond Aleph Nought, the number doesn't keep going. In fact, it doesn't even go to that level of countability above Aleph Nought. It effectively ceases and it is over with. Now, this doesn't prove this assumption, but it demonstrates how we use assumptions that are very similar to that in regular number theory and regular mathematics without even questioning it.